Hey, HL students. This is going to be a video lecture on non-uniform potential and non-uniform potential energy. So we're going to take the skills or the understandings that we've learned in uniform graphing, specifically talking about the area of a gravitational force and area of the gravitational field graphs as to find our potential energy and potential graph or values, and the slope of a potential energy graph and the slope of a potential graph to find, vice versa. So we recognize those, and it's important to know that what we define as a reference point before we move forward, because there's going to be a paradigm shift in what we consider a reference point. So um, when we think of like where do we want to find a potential energy from, we often don't really exclaim that we are recognizing that there is zero potential on the ground. We just kind of assume that to be true, but that we can't assume that anymore because that's not true anymore. So we're going to have to think differently through these concepts. Yeah, a paradigm shift is something when you have to change the way you think about something, the way that you maneuver through your understanding, so that we can more accurately depict what's actually going on. And so that paradigm shift is this reference point. But to do a quick review on this, I know we've hammered this in, but do a quick review. This idea is that as the area under the gravitational force graph is from, and one thing is it's from here, from some zero height to some other, as this point moves. So this point moves forward, then our area is increasing linearly. Therefore, we should have a linear graph for our potential energy. And the same thing goes for gravitational field strength. And then also that our slope here, so our slope is equal to our change in work over our change in height. And so we would be, mg delta h divided by delta h, so we get mg, we get the force. So that's okay. I feel like we're comfortable in that. There's one thing I want to address, and it's in these graphs. But first, let's just go over here because this is the one where you'll see the equation that I'm going to reference. The slope of this is delta v over delta h, right? That's the slope. And we said that this slope should, because it's g delta h, right? Because we've divided out the mass, g delta h divided by delta h. And that should be giving our g value, so we get gravitational field strength.
One thing you might notice though is this would be a positive slope, right? This looks positive to me, but our gravitational field strength is negative, which means we're missing a negative. So this should be the case. So our G should be negative delta V over delta H. And this is in your data booklet. So that's something to note. Similar for over here too, with the delta W, delta H. Just something to be aware of, but I think it becomes it's um, more obviously seen in the potential graph. And this is where we can branch off to do two things. We're going to have to understand where that comes from, because that equation doesn't really mean anything just staring at the equation. So I'm going to use what our understanding of equipotentials, which we did on Friday, to help us with that. But I also want you to see the graphs that we're going to be working with. So I'm going to quickly go to the graphs and show you what they look like and give you the equations for them. And then we're going to try to make sense of them. So non-uniform graphing, we've already done some non-uniform. So we're halfway there. We know that the Newton's law of gravitation is a inverse square. There's a negative, right, which is not in your data booklet, but that just means that it's attractive. And then there's a gravitational field strength, which is also negative, gm over r squared. We've already done those two. One thing on this graph to note, this I'm saying is like the surface of whatever mass we're talking about, right? That's the surface. Because weird things start happening when we go beneath the surface, because then we have weird mass distributions and things like that. So as of now, we're going to disregard in like below surfaces. So all my graphs will be imagining from a surface to some distance away. So we know from our previous uniform graphing that the area under a force graph, a force distance graph, gives us our work, and the area under gravitational field strength graph gives us potential. So that is going to hold true for this. But what gets weird is these graphs aren't so, you can't just look at the graph and know what the area represents. And so, like, if we think about the area under like this graph right here, if I were to draw this area starting from, and in this case, starting from 0, because we got to talk about a math equation, then like, what is that value? And well, this has an asymptote on the y-axis. So actually, this is infinite at the very beginning, and then it starts changing as you go forward. So the graphs that we're looking at are going to look like this, where this is a inverse square, and these are both just inverses. So our equations will be negative gmm over r for our gravitational potential energy, and just negative gm over r for our potential. The only thing different about them is the r is canceled out. Now, how we got to these two equations is not something that we're going to be able to work through. It requires a calculus, and you don't know that yet. But what we can do is give you a conceptual and diagramical, sure, visual way of understanding how we get from one equation to the next, because that's how we're going to understand this, not the math, right? The math sometimes is just good to know, but it's arbitrary unless you connect it to the concept. So first things first, let's talk about the slope. The slope of a potential distance graph, or the slope of a work distance graph, energy distance graph. And so I'm going to bring up this idea of equipotentials. Is how does the slope of a potential energy graph give us force, and then similarly potential to gravitational field strength. So I want to imagine look at two different locations on this topographical map, right? As we know, in a topographical map, these are all equipotential surfaces. So, and they have an equal increments going from line to line, right? So from like this line to this line is the same change of energy as, like, if I zoom in and say this line to this line. And we've already stated, and we're gonna look at this again, but we've already stated that the density of the potential represents the size of the gravitational field strength, or gravitational force. And I'm going to really zoom in and look at those sections and see, like, let's conceptually understand why, and that will give us a way to understand one of the graph translations that we just looked at. So I want to zoom in on like this portion, and then let's say in orange, I'm going to zoom in on like this portion. Actually, let's do it in blue because it's significantly different right there. And so if I go to the right and say, hey, if I were to look at my red portion, well, like, imagine you're standing on this topographical, on this surface. If you're in the red portion, you might see that this is extremely steep, right? Here you are standing, right? Going, how am I doing this? And that means you have a very large gravitational force going in that direction, or an acceleration, therefore an acceleration, and therefore, this is somewhat wrong, but a gravitational field strength. This is somewhat wrong because I'm giving you a situation in which we're standing on Earth. Your gravitational field strength is the same, but this is now a representation. We're trying to look at a topographical map and see it as a representation of a non-uniform field. That's the purpose of this. So therefore, if we have a larger f of g, well, let's just call it f of just f, right? That'll make it smoother. And then we look at the blue portion. We say, hey, those are distanced apart, which means it'll take, it's a further distance. You have to walk a further distance until you change potential energy. So your slope of the map, the slope of the surface, is smaller, and so if you're here, you have it, easier. There's a much smaller force pulling you downward. And so if we take this and use it to represent a non-uniform field, then we can see that the red will have a much larger change in potential per unit distance, per unit R, right? Because this is a 2D map, and we want to see it as a 2D map when we're comparing it to a non-uniform field. Because when we think of, and we want to visualize non-uniform fields, we think of walking or traveling radially inward to a mass and traveling radially outward to a mass. And if that's the case, then we're talking about a 2D plane that has the mass in the center, similar to just saying, hey, here's a mass, and here are our field lines going inward. That's a 2D picture, and that's the way we're going to visualize. So, great. There's a larger change in potential for the red person. And that would mean a larger gravitational field strength. Whereas the blue person has a small change in potential, and that means a small gravitational field strength and a smaller force. So that's our conceptual understanding of changes in potential, and then we could use it for saying change in potential energy. We've just multiplied both sides by m, right? We've multiplied both sides by m, and we've gone from a gravitational potential to gravitational field strength transition here. And then if we multiply both sides by mass, we get work to gravitational force. So, okay, that's our visual representation for slope. So I'm going to actually pause and give you another visual representation of slope. All right, this is a Desmos created graph that represents a slope, so a tangent line. So if we were to imagine, I can't draw on here because it's a Desmos app, but if we were to imagine that there was a very, very, very large mass close to the y-axis, right, or on the y-axis, and this was a potential energy graph or a potential graph, then we would see that the gravitational field strength is the largest, because the gravitational field strength would be the slope of this line, largest the closer we get, to the point where if we get super, super close, our line is going to become almost infinite, right? Which follows the idea that the closer you get to a mass, the larger gravitational field strength you feel. But the further you get away from the mass, the smaller the gravitational field strength gets, until at some point in time your R, well, actually I can't move it past this distance, but if your R were to reach a very, very large number, if the distance was, you're very, very far away from mass, you would not feel any force from that graph or from that mass, nor would you feel any acceleration or therefore gravitational field strength. So this is just the representation of that. This is how gravitational field strength change or gravitational force change. So we're talking about the slope. Okay. Now we're going to talk about the area. That's going to take some more time. So let's go back to our notes, and we have to talk about the area. So going downward, so we just showed that going upward, going from potential energy to force, it's the slope of the potential energy graph gives you the force, and the slope of a gravitational potential graph gives you the gravitational field strength, right? So like this right here, if I were to draw a line, actually let's just do it with line. Oh wait, it makes it, oh no, it worked. That is G. Well, that's negative G, right? Because that's a positive slope, and we said, hey, wait, that's not true, because our gravitational field strength should be negative because it's attracting, and so we know that our G is equal to the negative change in potential over change in distance. Okay? So, good. So this definition we're going to look at now and say our gravitational potential energy is the work done to move a test mass or point mass from infinity to a point in a gravitational field. So the change in our definition now is not just the work or the energy that an object has at a position. That's arbitrary for us now, because what we need to find is how much work is being done to move between 2 points, and in this case, it's from infinity to some point, right? Now, this is an arbitrary value, but we're going to use this to represent gravitational potential changes in energy, which is what we care about the most. I mean, infinity doesn't matter to us, so we're going to look at between 2 points, but we need to start here before we do that. So when we go up here, we know that the area under this curve represents gravitational potential energy. This gets a little harder, like we said, because where is the area start? But we want to say, well, how can we compare it to what we already know? So we've said, hey, on the surface, our potential energy is 0. So we like to define our potential energy as coming from some reference point where our potential energy is 0. Now, this is when we're on the surface or at the center of the mass, our potential energy is not 0, as we can obviously see. So we want to find where both the potential energy is 0 and the force is 0. And the reason why we want to do that is because we want to find where is there a 2 points in which if we move between, no work is being done because no force is felt. And the only place that exists is way down here. And I can't even show it, right? Because it's some distance where r is equal to infinity. So it just keeps on going. Now, this is where there's a few weird things. One, what do you mean a point where it's we're at some infinite distance away? Like, you can't just walk through, walk 3 meters and say, hey, now I'm at infinity. No, that doesn't happen. So this is definitely an abstract thought that we just say, you know what, it's so far away that force is negligible. That's what we define as infinitely far away. And therefore, it is infinitely far away. So when I move between 2 points at that distance, I don't have to oppose any force, right? I don't have to worry about a force. So that's where my force is 0, and my potential energy, also when I get to some point infinitely far away, is also 0. So the definition is the work done to move a test charge from infinity to a point. So that means that definition is, if I were to shade in this area up until some distance, r prime. So this number, all that tells you is how to find that's the work done to move some object from infinity to a point. But we don't care about moving it from infinity. We want to get rid of that. So we're going to have to use potential differences to somehow find a way to say, hey, I want to cancel this area because I don't want it. I just don't. So we want to find, hey, what if we move between here and here? Let's call S goes to R1 and R2, right? Or R initial and R final. So what is the area to get there? Well, that R1 is the total area, and R2, let's do it in red, R2 is this area. So if I know the potential of 1, which is the area to R1, and the potential to R2, then I can subtract those two, and what I'm actually doing is I am canceling out this area, and I'm just left with some area between R1 and R2. So what I just said, it might be a little tough to see, so I've got another visual representation of this. Before I move forward, recognize that whatever I do here, all I have to do is divide my test mass, my little m, out, and the same thing applies over here. So there's nothing different about how we move downward this way, right? Yeah. So the paradigm shift is the weird point of I'm coming from some point infinitely far away, and it has to do with the idea that I'm not feeling any force there, and therefore I'm not doing any energy. That's the reason. And then the graphs are in such a way that it's more mathematically correct. So let's show this this other visual representation that I have. So a change in gravitational potential energy, or change of potential, these are these situations will work, this representation will work for either, is just the change, right? From some initial position to some final position. So first, I'm going to ask you a question. Would there be a positive or negative change in its gravitational potential energy moving it from some initial point to some final point? So let's say the green is the initial position and the blue is the final position. And is that negative or positive? We're going a further distance away, but this graph is negative. So I want you to just come up with an answer and maybe a little bit of reasoning, and then let's see what we're thinking, because I want you to think you could use the intuition that you know previously. So our potential difference is a final potential minus initial potential. So I want to start with my final potential, which is supposed to be a blue dot, but I made a mistake. So we just know that that is the final position, right? So that should be blue. Let's just draw it as blue. There we go. Let's give this a number. Let's actually just give it a number. It's wrong, but I just want to make up some numbers. So all I know is, well, the area is in the negative axis, and it's smaller than our initial area. So let's just say it's -1, the smallest negative number we can. And then our initial, well, has a larger magnitude. That's important, larger magnitude, but is also negative. So this is -3. So when I subtract these, I get -1 minus -3, which will equal +2. So this area is actually +2. And that is, I mean, obviously not +2, but we're just making numbers. But that's going to be either my work to move me between those 2 points, between the initial and final position, or the work per unit mass, depending on which concepts we're working with. And you might say, hey, that's weird. That's a negative area. But what we have to really think about as well, we are moving between 2 points. So there are 2 options. We can move this way, or we can move this way. And when we do either way, they're going to give us, one's going to give us a positive and one's going to give us a negative. Now, why do we like this to be positive? Why do we want to say that when we move from a position close to a mass to a position far away from a mass, we are getting a positive change? Now, there's 2 reasons I'm going to say why this is a good thing. One, it follows the intuition that, hey, if we're in a uniform field and I lift an object up, then I'm giving it potential energy, so it should be gaining. It should be positive. So those 2 still match, so that's fine. And then the second reason is, well, it's actually just that one, because I'm not sure if the other one I'm going to say has like a direct meaning. So yeah, we just like to think that it gains potential energy when moving away, which makes it really weird, because that means that this graph, and this is what we have to overcome, is as we're moving further away, even though it looks like the numbers are getting like smaller, like let's say this is -2, and then this is like -6. Well, because I'm moving from some -6 to some -2 value, I'm increasing, right? That's a positive change as I move further away. It just so happens I'm dealing with negatives. So that's the only annoying thing that we have to deal with. But recognize that your intuition of increasing energy as you move further away is still true, and we'll be good. All right, so that's gravitational field, gravitational potential, gravitational force, and gravitational potential energy, and how we move through those in a non-uniform field. We're gonna definitely take some time in class to work through this and have activities that hopefully give you this understanding a little bit more intuitively, a little bit more something you can connect with and think about. But we do have to talk about electric fields and electric potentials, and I will go there. I'm only going to briefly connect with it because it's the same. It's the same as the gravitational potential. Just the only thing that changes is we're dealing in the positive axis. So here we have an electric field, which is kq over r squared, which is nothing new. And so when we look at this, we have 2 things we want to think of, right? So this is a electric field, similar to our gravitational field up here. So the area of this curve should give us our voltage. and that's what we get. So we get the same transition of KQ over R squared becomes KQ over R. And then you might see, this graph shows you the inside. One thing to note, and there's mathematical proofs for this, and I will share it with you when it's necessary, but the electric field inside of a charged hollow sphere, that's what we're looking at, is a charged hollow sphere, is 0, and that must mean that the slope, right, the slope of here, slope is equal to 0, that's why we have a constant voltage inside, and then it decreases outward, decreases proportional to 1 over R. As well as when we look at the slope of our voltage graph, we still have the same relationship, and this is in your data booklet, that the electric field is equal to the negative change in voltage over change in R. So if we were to look at like this position and draw a line right here, well that is, right, my slope looks negative to me, so I should get a positive value at that position. And that should give me like some R away, would give me some R away. And that's going to give me the point, right? The slope of that line would give me the point at this position, the Y, the value of the electric field at that position. So this still matches completely the same. So that sums up this topic. I recognize that this is a complex topic to think about. So do your best at understanding what I've said. Use Cognigy for extra support, and you will need to ask us questions, and we will need to have activities that will help you, think through this, as well as practice problems. But really, before I end this video, I just want to say that use your intuition of the areas and slopes in uniform fields to help you with this, with non-uniform graphing, and then you just have to think about rates of changes, and specifically rates of changes when it comes to non-uniform fields, like this representation of a non-uniform field. And that's it. We'll see you in class, and we expect to have questions. So good luck.